Geometry lesson 1-1. First example, looking at patterns. Given these three shapes to look at, can we decide what the fourth term would look like? So we have a shape that looks as if it's maybe oriented pointing up. The next one's pointing to the left, and then the third one is pointing down. Because this says the fourth term and I see three visible shapes, I'm going to make the conclusion that this is representing the first term, the second term, and the third term. Therefore, the fourth term, hopefully if this continues, it appears as if it's rotating 90 degrees counterclockwise each term. We're hoping that the fourth term, these two, will be oriented pointing to the right. And as we can see, that is in fact the case. We have the two pointing to the right. Now, if it had not said, what's the fourth term, if it had just said, what does the next shape look like, then maybe my interpretation could be different. I might think that all three of these are one shape together, and then possibly I'd be looking at this scenario saying, here's one shape, followed by the exact same shape, followed by the same shape, and finishing up with the same shape, and so on. Maybe the fourth term would look exactly the same, assuming that one of these is one term. All three of them together is one term. So it just sort of depends. But because, again, this one said the fourth term, I'm going to make the assumption that this is the first, second, and third term, and that my fourth term would look like this, with 90 degrees being the counterclockwise movement. We have a few definitions we just want to make sure that everybody's clear on. First is a conjecture. A conjecture is an unproven statement based on observations. We make numerous observations throughout the day. One of the examples that I've used is, typically speaking, teachers are fairly habitual, and that we like to park in the same parking places each day. That doesn't mean it always happens, but if somebody were to observe, they would be looking at me saying, oh, Mr. Corey always parks there. All it takes is for me to park somewhere else, or someone to park in my space and force me to park somewhere else, and then this conjecture is no longer true. It's not based on fact. Fact would be like water freezes at 32 degrees. Therefore, if I look outside and see a temperature gauge that says it's 32, I'm going to make the assumption that water is now currently freezing outside, because that's based on the fact. Yes, I observed the thermometer, and it could be wrong, but I'm not making my conjecture based upon anything other than the observation. In that case, it would be not a conjecture at all. It'd actually be, I'd be basing my hypothesis on the fact that it was 32. That's what I'm basing it on, not necessarily that I actually know what the temperature was. From the conjecture, we're actually using inductive reasoning. Inductive reasoning is the concept of looking for those patterns to make those conjectures. And we do this all the time. I also spoke in class that when I was playing basketball in college, I actually watched my opponent to see if he had any tendencies. Those tendencies were from my observations, and then I would make conjectures based on those observations. He's very right-handed, likes to shoot from the left side of the court, wants to cross over before he goes anywhere. Anything like that I would use to my advantage. Didn't mean it would always happen, but it was based on my inductive reasoning. A counterexample. A counterexample is something that we would find that shows the conjecture false. In the case of me not parking in that location would then prove the conjecture of Mr. Corey always parks in the same spot false. It just takes one. I don't have to find five counterexamples. I just have to find one counterexample. And that one counterexample is all it takes to prove the conjecture false. Again, it was based on observation, not based on facts. And our final definition is Goldbach's conjecture. What's different about conjectures, and it's sometimes hard for people to understand, is it may appear that it is in fact true, and that it is a fact. For example, Goldbach's conjecture says that every even number that is greater than 2 can be written as the sum of two prime numbers. So if I were to take an even number like 4, 4 is the sum of 2 and 2, two prime numbers. 6, another even number, is the sum of 3 and 2. I'm sorry, 6 is 3 and 3. That would be two prime numbers. And this appears to be true all the way throughout. And we could sit here for days and days and days and keep trying and trying all the even numbers, and we'd always be able to have, like this one, 44 is the combination of 13 and 31, two prime numbers. But because we cannot actually test every single possible number that's even, because of infinity, it just keeps on going, because we can't prove every single one, it has to stay as a conjecture. even though we may test a million of them and it works, we still have to say it's a conjecture because the next one we try might be the counterexample. So that's sometimes a difficult concept to grasp, but the fact that it's a conjecture is it's just that one, we can't prove it all the way. So therefore it's not Goldbach's law. It would be his conjecture based upon the fact that no one can prove it. And believe me, there are people who are trying to prove all of these. All right? I could make it up. I could say every single even, if I take two odd numbers and add them together, it always makes an even. So I can say 1 and 3, yep, 4 makes it, that's an even number 4. 5 and 7, yep, add together to make 12, that's even. And I could say that, oh, that seems like it's always going to be the case, and it most likely is. But because I cannot actually prove it by trying every single possibility to prove that it works, it'll maintain itself as a